Um, all right, so I kind of want to just take a step back and look at where we were. So from exam number 1, you don't have to write this part down. Exam number 1, we went into the atom as well as the quantum mechanics of stuff. For exam number 2, which is next week, we went into 2 atoms making a chemical bond or more, and then what do they actually look like, as well as what their property, where the electron is located, and so on, as well as how to name them. So number 3, we're actually going to look at reaction now. All right, so we're just going to go from the smallest and get bigger and bigger. That's more or less kind of what I'm trying to get to. So part 3 is basically chemical reaction. Same as before, we have a couple of weeks or so of material, and then there might be an exam. And if we don't have enough time, I'll eliminate exam number 3, and instead we're just going to have a 1 bigger final instead of 3 midterms and 1 big final. Depends on how confident I am that we captured everything that I want to cover for this particular part. But for now, we want to balance the chemical reactions. You've already done the balancing reaction with these ionic stuff, and you can think of them as the simplest possible type of balancing reaction. So we have iron plus 2 plus PO4 3 minus, and it turns into Fe3 PO4 2. Right. So we've already done that type of balancing reaction, and in fact you've done it throughout this the previous worksheet. And essentially the way to balance this out is that you need 3 iron and then 2 phosphate. In this case you balance it to look like that, right? Essentially we're just going to expand the same concept on a little bit more complicated reaction. And if you're looking for the pages in terms of the class planner, go to page 66 is where we are. It's the new sheet that I just printed out for today. We're skipping a few things here and there, but we're just going to jump right into chemical reactions because the first portion of that handout is this whole thing, which you guys already done, and you've already named them as well. So how do you balance chemical reaction? There's a lot of different ways it could be done. It could be taught, and I'm going to show you 2 different ones. One of them is the fast one. So method 1 is the fast one, which I like to call the ping pong one. And it's really fast, but it doesn't work all the time. So I'm going to show you something else that's slower, but works all the time. And essentially the ping pong one is just like playing ping pong. You go back and forth, and you balance it as you go along. So for example, I'm just going to start from the beginning, from the left-hand side. So I'm just going to start and look at the iron. So if I look at the iron here, I have 1 iron molecule, and I'm going to go to that side, and I see that, oh, there's also 1 iron molecule. So the way to balance it out is that they match 1 and 1. So I'm just going to put 1 on both sides. And then the next one is that I notice that this particular iron is bonded to hydroxide, or OH minus. And specifically, I have 3 OH. So I'm going to look at the reactant side, and I'll find that there's an OH there. But on the product side, I have 3 OH, but on the reactant side, I only have 1 OH. So I have to balance it out by giving a number 3 on this side. And to match out that I have 3 OH on both sides. So now that's good, and we're going to move on. Now this OH is now bonded to an NH3, or sorry, an NH4. What is the name for NH4, by the way? Ammonium, thank you. And we're going to go from the ammonium, and we'll look at the other one that has ammonium on it, and we see that it also matches because it's a 1-to-1 ratio. So we're going to give it a number 1. So far we have coefficients on each one, 1, 3, 1. Hold on, I made a mistake here. Oh, sorry. There's 3 NH4, excuse me, so I have to put the number 3 on the other side. There you go. That's what I was missing, 3 and 3. And we pretty much balance the chemical reaction. And if we look at and count the number of atoms on each side, I start out with 1 Fe and 3 Cl. And over here I have 3 of NH4 and 3 of OH. And if you try to count everything in the end, you'll find that the same number of particles before and after is true. Therefore, the reaction is now balanced. So this is the fast one, and I like to call it the ping pong one. And majority of the time, this is what you should do. Just kind of try to match it. 1 iron here. I look at in the product side. There's another 1 iron. We put a 1 to 1. This one is bonded to an OH. I go over there. There's 3 here, so I'm going to put 3 over there. This OH is bonded to NH3, and I have 3 NH3. And if I look at on the other side, there's only 1, so I put 3 on the other side. So just keep going back and forth, back and forth. Now, the next one that's a bit longer to do is this one here, the algebraic one. And it may not be particularly clear what the A, B, C, D on the side here. So I'll do that with you as well. Just slow it down a bit. So the chemical reaction is that we have PCl5 plus, we don't know how many stoichiometry, H2O, and these two will react and turns into phosphoric acid and hydrochloric acid. We can still do the ping pong one, but I want to show the algebraic to be to give you a slower method, but it works all the time. So let's say this is A. We don't know what it is, so I'm just going to call this stoichiometry A, B, C, and D. And the idea is the same. The number of particles that we start out on the reaction side must be equal to the product side. And we're essentially going to make an algebraic equivalencies between one to the other. So the first thing I'm going to do is I'm going to go and look at the phosphorus. Look at phosphorus. Here we have PCl5 on the reactant side, and the product side we have H3PO4. Notice that there's 1 phosphorus and 1 phosphorus on the other side too, right? So the ratio is 1-to-1 ratio. So I can say that the quantity A here, because I have A number of phosphorus, is equals to C. So I'm looking at the phosphorus is C, is A, and I basically look at the stoichiometry. 1 phosphorus here, so C, 1C, 1 phosphorus here, 1A. So that's my first equivalency. And then the next one, we can keep going and look at every different molecules that we have. I'm going to look at chlorine here. Notice that here I have 5 chlorine. So I'm going to write down on this side 5A. And the chlorine now is bonded to D, and there's only 1 of them. 5A is equals to D. So that's my second equivalencies. So far so good? Yeah? So if I were to look at hydrogen, what's my equivalencies going to be? Notice that the hydrogen shows up twice in the reactant side. Once in the reactant side, but twice on the product side. So in the reactant side, I have H2O. So I should put in 2B. What is 2B equals to? Almost. 3C plus D. Yeah. And the last one is the oxygen one. B is 1 oxygen, so 1B is equals to 4C. So again, if I go back to the hydrogen side of things, 2B, so it's right there. And here I have 3C and 1D, and I'm just going to add it up all together. So that's basically it. And then we're going to guess a number for the value of A, B, C, and D, and so on. And then we're just going to go from there. Any questions on the equivalency stuff that we have so far? We're going to try to substitute a number in each one, right? So we're trying to put a number in A, B, C, and D. So we're just going to guess a number for now. We're going to guess, a pretty decent guess is that, notice here is that 5A equals to D, so I'm just going to guess that A equals to 1. I don't know whether it's going to be correct or not, but I'm just going to guess and see what happens. If A equals to 1, so C is equals to A, so C must also be equals to 1. And if A equals to 1 again, D is equals to 5A, so therefore this must be equals to 5. 5 times 1. The next one is, I'm going to skip this one for now, and I can go down here because it's a simpler equation. For C is equals to B, so B must be equals to 4 times 1, because C is equals to 1, so this is 4. So now we have the values for both A, B, C, and D, and that's basically the balanced chemical reaction. So 1A, so A is equals to 1, B is equals to 4, C is equals to 1, and D equals to 5. So that's the balanced chemical reaction from here. So far so good? Yeah. I want to show something else while we're on the same page. The equivalency is still the same, but suppose what happens if we were to guess incorrectly? What happened to the whole value? So let's say, sorry, I'm giving myself extra space. So suppose that I guess incorrectly and say, oh, I guess that A equals to 3. Well, if A equals to 3, C equals to A, so A equals to 3, D is equals to 15, B is equals to 4 times 3, so that's going to be 12. Notice that it's the same ratio as before, so now we have 3, 3, 15, and 12. What I'm going to have to do is I'm going to have to remove common, or I should say divide by common factor. And if we do that, this becomes 1, 1, 5, and 4. So it's still the same thing, right? So even if you guess incorrectly, just divide it by the common factor and get rid of the fraction, you'll get the same right answer in the end.
Should we always just guess that A is 1?
Sometimes. Yeah, ish, no, depends. If you realize that some of the ratio is like 3 and 1, and you might want to choose like a number 2 or 3, but in the end it doesn't matter. You'll realize in the end, if you guess incorrectly, it'll be 1 over 2, 1 over 2, 5, and 1 over 2, then it means you have to multiply everything by 2. So it doesn't matter what you guess, as long as you remove the common factor, as well as make sure that they're just pure integers. Right. That's about it in terms of the algebraic method of balancing reaction. So, any question here? Again, sorry, I shouldn't move on too fast. Yeah, no? The best way to go, balancing reaction, try to do some of these. I would say do number one just for the sake of time. Do number one. Do number four. So we'll go easy, medium, and hard. And then we'll do the last one here, the medium one. So number one, number four, number five, and number seven. And if it says easy, that means you could probably just do the ping pong one and you'll finish it very, very quickly. So what do you get for number one? Just read out the number for me, please. Do you get the same thing? 1214? Yeah. That should be the fast one to do. Oops. Oh, this is wrong, actually. There's 2 oxygen. I'm just going to go from here to there. Number 3. Oh, sorry. There should be an easy one. The best way to think of them is try not to count all the sulfur and whatnot. I'm just going to count each one as a single unit. So notice here that there's 2 SO4.
Yeah.
So this needs to be a 2.
Right.
Right. So just count the SO4 as a single unit. So I think that was the initial.
Well, there, then I mean that's.
So I'm usually just going to start from the left to the right, and we go from there. The hydrogen shows up twice, so I'm not going to try to balance these. I'm going to move on to the sulfate, because it only shows up once.
Okay.
So we put a 2.
Great.
Then the lead, and put a 1 in the front.
Because it only shows up.
Yeah, it shows up once, so 1 and 1, so put 1 there too.
Yeah.
And we have now 4 oxygen attached to here, like 4. So there's only 1 here, so put a 4.
Then here there's 8.
But we already take it into account because the SO4, the sulfate,
okay.
comes as a single unit.
Okay.
If you try to break it down, it becomes more complicated. So if you think of it as a polyatomic single unit, it's easier. So if your atom shows up more than once, try not to balance those first, because it makes it harder. And if the ping pong method doesn't work out in the first pass, then try to balance it out. It'll take longer the first time around, but you're trying to do number, that one?
So I have 6.
So why don't we try to look for it? Right. So we're going to start from the left to right, so it's easier. And notice here that the oxygen shows up for question 2 twice in the product side. I'm not going to try to balance those. So I'm going to go from here to here. There's 2 here, there's 1 here, so I'm going to multiply by 2. Yeah? And I'm going to skip the oxygen, I'm going to look at the chlorine. There's 3, and there's 2, so 6 in total.
So put 6 on this one.
6 on this one, which is what you did. And then we can look at the hydrogen now. There's 6 hydrogens in total. There's only 1, so I'm going to put, 2,
We did
3. And then we're good.
three.
Yeah. So 1, 6, 2, 3. And if you try to count the oxygen, to just double check because we didn't try to balance it, we have 2 here, and we have 3, so we have 5, and there's 5. So we're good. Yeah. So yeah, that one is one of the easier one. And see if you can try to get to number 7, or even skip to number 7. Usually when your quantity is, there's 10 of stuff, 7 of stuff, and it shows up multiple times, that's when things becomes annoying to balance. And in this particular case, I would probably just go directly into the algebra. proper one should be 12, 3, 4, and 6. 12, 3, 4, and 6. What's that? B is equals to 3C divided by 4. And then it depends on how you start out with your guessing number. So what did you guess for A? Did you can I just double check? What did you get for number 5?
That's where I got A, C, and D, and D. I probably miscalculated somewhere.
For the phosphorus, why is it 4B equals 3C?
Why is it that one? 4B. And
I got 4B equals C.
oh, equals to C. Yes, sorry. So that was my error. Okay, let's do this again. So, okay.
You're right. Well, besides that, it's like what I said. It's the 12, 1,
Okay.
6.
Okay. So it'd be 12, 1, 4, 6?
Mm-hmm.
Okay. Yeah. What did you guess A equals to initially?
3C.
No, what did you guess the value to be?
Oh, 12.
You immediately guess A equals to 12?
Oh, I get what you're saying.
Oh.
No, I did, for this one, I did the algebra at the beginning.
Okay. Yeah.
Does that
Doesn't-
make sense? Yeah, I did guess a number at the beginning.
Okay. So whatever works. If it works for you, then it's good. If it doesn't, then find something else.
But yeah, for this problem, what would you guess? 3 or what?
I would guess A equals to 3 because if I say A equals to 1, C is immediately 1/3. So I might as well just guess 3 to get rid of that fraction. So
Oh yeah, that makes sense because fractions is more annoying to deal with.
yeah.
Okay.
It doesn't matter really. If we guess A equals to 1, C is going to be 1 over A.
Yeah.
So it's going to be, it's going to be 1 over 3. And if you look at D is going to be A divided by 2. So this is going to be 1 over 2. And then I'm going to skip the big equation here, and I'm just going to go to the bottom. C is equal to 4B. B is equal to C divided by 4. And it's going to be 1 over 12. So this is the biggest factor, so I'm just going to multiply everything by 12.
Yeah, it's weird. I don't know why my brain decided for the hard one to automatically just do algebra instead of putting in guessing a number.
Okay, that's fine too. What? Yeah, it works.
Number 9. Is number 9 now? It's okay.
Number 9. Is number 9 one of the medium one?
Yeah.
So when I say medium, it probably means that you can get by with the ping pong one, which I'm going to try to do now. And if it doesn't work, then I'll go to the next, to the algebra. The way I would do this is that I notice that the calcium shows up twice in the product side, so I'm not going to try to balance the calcium and instead look at the phosphate. So there's 2 phosphate here and 2 phosphate there, so I'm going to put 1 and 1. And then we're going to look at the hydrogen next. There's 4 hydrogen, and here there's only 2, so I'm going to put 2 over there. Now that there's 2 sulfates, I'm going to look at the sulfate here. There's only 1. I put a 2. So whenever you see something that shows up more than once, skip that one, and try to find something else that's easier. So in this case, it's 1, 2, 2, 1. Or if you want to use the one that you skipped to check your result, then it's a good way to go.
Oh, with algebra, like A equals 1.
Yeah. So no. I mean, like, since we didn't balance calcium in this particular problem, I can see that there's 3 calcium here, and in the end I have 2 calcium, and 1 calcium.
Mhm.
So it's properly balanced. All right, what are you right now? Yeah.
This one?
Okay.
This one?
Yeah.
I'm on this one.
Oh, hold on. Can I see anything? Yeah, that looks right. Yeah, you don't have to balance everything, but let me just kind of spot check. If you got one, um, that one? Yeah, 12,146. Hold on. 12,146 or 12,416? Sorry, I don't remember. 12,146. So I think you get it right. You just switch around the A and the B and the C. Somewhere in there you forgot that this is supposed to be C and this is supposed to be B. That's my guess. But yeah, otherwise it looks okay. And oh yeah, I forgot to do number 17. I mean number 7. This one I'm going to do this ping-pongy way. So there's 8 carbon there. I'm going to put 8 and 1. And there's a bunch of hydrogen here, but the hydrogen shows up multiple times. So I'm going to skip that one. And instead I'm going to look at the oxygen because it only shows up once. I have 8 oxygen, so I'm going to put 8 here. Now I have hydrogen that I have to balance. There's 18 plus 2 plus times 8, so that's going to be 16. So the sum is 34. And it's going to be divided by 2, so 17. So yeah, I'm right. Number 8. I have 2 nitrogens and 2 nitrogen here, so I'm going to put initially 1 and 1. And then I have 4 hydrogen, only 2 there, so I'm going to put a 2. And the last one here, I have 3 oxygen, I have 2, so this is going to be 3 over 2. So clearly we have to get rid of the fraction, so it's going to be 2, 2, 3, 4. Angel, I think I misread that question. No, you got the same thing? Okay, good. So I think I wasn't as I didn't pay as much attention as I should. Yeah, so get rid of the fraction. So I think we're probably okay, and it seems like you guys are doing it just fine. If you can do the ping pong method, just do that first, because the algebra one takes a while. And I would say 80% of the time it'll work out just fine if you just do it the ping pong way. Whereas the algebra is when it's huge. When you see a bunch of numbers like 12, 17, and so on, that's when you may want to double check your result. So the next portion that I want to go to, we still have about an hour, is equivalencies. So can you read for me what the balanced reaction for number 1 was again?
1, 2, 1, 4.
Sorry, can you read the reaction, please?
Oh, SiCl4.
Hold on. What is the proper name for that?
Oh.
Silicon tetrachloride plus how many what?
H2O.
How many water?
Oh, 2.
2 water turns into
1 silicon dioxide.
Yeah, silicon dioxide and
4
HCl is
hydrochloric.
hydrochloric acid.
Hydrochloric acid.
Yep, so that's the acid. So if you go to the next page, how many moles of SiO2 or silicon dioxide is produced from 3.2 moles of SiCl? So if you start out with 3.2 moles of SiCl4, how many moles of this guy would you produce in the end? If you start out with 1 mole of silicon tetrachloride, how many moles of silicon dioxide would you produce? Yeah, it's the same thing, right? If you want to look at it a bit more mathematically, you can think of the balanced reaction that you made is just the recipe. If you use 2 eggs, you make 3 cakes. So the best way to go is that we start out with 3.2 moles of SiCl4, and I'm going to use the recipe here, which is exactly what it is, and use a bit of unit conversion factor. So I have 1 SiO2 is what I want to know. So how many moles is SiO2? And the balanced reaction is 1 SiCl4. So it's the SiCl4 cancels out. Sorry, let me do it this way. The SiCl4 cancels out, so we ended up with just moles of SiO2. Okay, so 3.2 mole SiO2. That's basically it. It's just a ratio. If I were to give you asking the number of moles of HCl, then the ratio is 1 to 4. Then you multiply it by 4, divided by 1, so you get the same 4 times as much. So this one is pretty straightforward. Let's keep moving on. For number 5, or actually for number 4, can you read me the balanced chemical reaction again for me, please? It's the one with the, I know there was 17 oxygen. Turns in.
Well, it's HCl.
8 what?
Yeah, 8.
Number 4, then.
Oh,
Number 4.
Sorry. I thought you said it was
Oh, no. No, number 4. Any of you guys balanced number 4?
Yeah.
So 1 mole of CH4 plus 2 moles of oxygen equals
1 CO2,
1 carbon dioxide, 2 water.
2 H2O. Okay. So the question is, if you have 1 moles of CH4 reacted with excess amounts of oxygen gas, how many moles of CO2 would you produce? Oh, I should have used the more complicated one instead. But anyway, so you basically just look at the ratio. If you get 1 of these, then you produce 1 of that. If you use 2 of these, you produce 1 of that. So the balancing is fairly straightforward. And that's more or less how to use the balanced reaction to get the number product that you should get in the end.
My question is,
Yeah.
how many moles of HCl?
So what was the balanced reaction for?
Oh, wait, never mind. Sorry, I'm doing the wrong math.
Yeah. So number 5. What's the ratio between HClO4 and Cl2O7? 2 to 1. Okay. Then we get 2 to 1 ratio. This is based on the previous problem. Balancing stuff. So I think in this particular case, it's no big deal because it's really is straightforward. You just look at the recipe. You need X much of flour to get X much of stuff. Now the next portion, if you go to the next one, is the limiting reactant type of problem. And I think I should change that example because it's a bit confusing. So let's do another example, the example from number 4, which is we have 1 CH4 plus 2 O2 turns into CO2 and 2 H2O. So suppose that we start out with, so what you want to remember is that your balanced reaction is a recipe book. It's not the same thing to what you have in your pantry. You have a cooking book, but you might realize that the amount of egg that you have in the fridge is not the same thing as what you have in the recipe book. So suppose that you start out with 5 grams or 5 moles of CH4 and say 17 moles of oxygen. How many moles of CO2 that you can produce? What is the maximum amount that you can make? And by observation, how many moles of this can you produce? 5. You should get 5 in the end. Now the reason for that is that if you look at the number of CH4, if we look at the ratio again, this is 1:2 ratio. So in order to consume all of this 5 moles of CH4, we would need 10 moles of oxygen needed. And in our actual reaction chamber, we actually have more than what we needed, right? And that's why the amount of product that we can get is going to be limited by this amount. So essentially, there's a couple of things in terms of terminology. We have more than what we needed, more than needed. So in this case, whatever it is that we have more of is going to be called an excess. Oops, my X keeps disappearing. It thinks that the X is I need to erase it. So sometimes it's just erased on its own. This is excess reactant. And the one that we don't have enough, this is don't have enough, is going to be the limiting reactant. There's a slightly easier way to think about this whole thing. Which one is the limiting reactant and which one is the excess reactant, which is just divide what you have with the recipe. And we have 5 moles, and if we divide by 1, which is the recipe, versus 17 divided by 2, you'll realize that this is going to be bigger. So whatever is smaller is going to be your limiting reactant. It's as simple as that. It's whatever is smallest is going to be your limiting reactant. And you can then figure out the amount of product that you can produce in the end that way. So let's actually start to jump in to one of this product problem that we have here. Might as well. So suppose that the chemical reaction is given on the top here. So PCl5 plus 4 H2O 1 produce 1 phosphoric acid and 5 hydrochloric acid. We have 7 moles of PCl5 and 23 moles of H2O. So by observation, which one is our limiting reactant? Water. Yeah. So 23 divided by 4 is equals to 6-ish or 5-ish. Whereas this one is 7 divided by 1, so it's going to be 7. So water is going to be our limiting reactant. So if we want to know the maximum amount of stuff that we can produce, we are going to consume all of our limiting reactant. If 23 moles of H2O is consumed, how many moles of H3PO4 can we produce? Well, that is pretty straightforward. We start out with 23 moles of H2O, and we're going to multiply it by the ratio. We have 1 H3PO4 divided by 4 H2O. So it's just going to be 1/4 of what it was before. I don't know what this is, but this is going to be 23 over 4. So I'm going to be a bit lazy there. So we're going to produce 23 over 4 moles of that. And in terms of the HCl, what we can produce is going to be 5 times 23 divided by 4. right? Because if we look at the ratio for HCl, we start out with 23 moles of H2O multiplied by 5 HCl for every 4 H2O. So it's going to be whatever it is, 23 times 5 divided by 4. And we're going to put it right there. And the last one is the same for PCl5. Whatever that is in the end.
Do you like whole numbers?
Sorry?
Do you like whole numbers?
No, I don't mind, but I don't have a calculator, so I just leave it as a fraction for now. So, any clarification? Because it is going to be, yeah. If you need clarification, let me know, and where I got all these numbers from. Yeah.
I see. So
It's the initial, and then this is a change, and this is going to be end state. So initially we have 7 moles of PCl5 and 23 moles of H2O. And what is, if all of our H2O, which is our limiting reactant, is consumed, the change is going to be minus 23 because all of them is consumed. And in the end, we should have 0 H2O left. Yeah. And if we look at the PCl5, we start out initially at 7 moles. And then we're going to subtract 23 divided by 4. I don't actually know what that is. The end state, the number product that we get in the end is going to be 7 minus 23 divided by 4. I'll leave you with the calculator in the end. Now, in terms of our product, which is the phosphoric acid as well as the hydrochloric acid, notice here I put a positive sign because we're producing our product. So instead of it's going to increase over time, therefore it's positive. So we're going to have in the end 23 divided by 4, and then I think that's 115 divided by 4, whatever that number is in the end. So I for initial, C for change, E for end.
we start off with 0 on the product side because they didn't give you a rule.
Right. Right. So
But if they did,
yeah, if it starts out with a non-zero number, then you just add it up together. Any questions so far? Yeah? No? It's a bit of a review, and if you've taken chemistry class, most of the time your teacher would have tried to drill something like this in, because it really is the basic of chemical chemistry. You make something, you mix something together, you want to know how much you get in the end, and how much is left over. Right, so in this case we have leftover. Do you mind if I erase this now? Yeah? Yeah? Alright, so suppose that instead of all of our limiting reactant is consumed, so we start with 0 in each one of the product, instead of only 23, only partially consumed, so partially. So what happens if we were to subtract an X amount? Let's do an X amount of H2O is consumed. So how many moles of H3PO4 will we produce in the end? How much is the change in terms of X? So we still have the same thing. We have X mole of H2O. We're going to multiply it by the ratio, which is 1 H3PO4 for every 4 H2O. So here, it's going to be X divided by 4. So far so good? Yeah. And we can keep going. So what is going to be for the one in HCl? The ratio is going to be 5/4. So therefore this is going to be 5x over 4. And if we look at the PCl5, the ratio is 1 PCl5 for every H2O, so this is also going to be 1 over 4 x. And in the end state, we just do the same thing. 7 minus x divided by 4, 23 minus x, x over 4, as well as 5x over 4. Now there's, I do want you to get comfortable with this more abstract result rather than actual number, because we're going to use this for acid-base reaction.
Give an example of that right below, just with the A column being the limiting.
Right. And this is just an example that this is the limiting. Or really, it really doesn't matter whether it's limiting or not. We're just defining x to be this one. But it doesn't matter. As long as you understand the concept, it's just the mole ratio before and after. Anything for me in here? If you don't have any questions, I'm going to keep moving on. We still have an hour left, so let's see how far that we can get through for today. A bit of it is review. Yeah, you guys could do that on your own. It's fairly straightforward. Limiting reactant, stoichiometry, mass and moles. I think this is okay. All right, so there's another thing I want to mention. I want you to try to do this one here. So page 72 on the thing. Sorry, my bad. Page 71. I want you to try to do page 71, part 1. Here. So let's try to do this whole thing as a single large problem. Before we begin, do you guys know what a molecular weight is? Okay. Okay. So let's try to do page 71. All the way from balancing reaction, limiting reactant, converting things from grams to moles. And my suggestion is that your limiting reactant, or actually for any kind of chemical reaction, just convert everything to moles. So notice here it starts from gram. You want to make sure that you convert all the quantity that you're given into moles first. So convert to moles. And I'll try to do this together too. So what's the molecular weight of octane, C8H18? 114? Right, let's see. Oh, let's just round it up easier. We have 8 carbons and the molecular weight is 12 grams per mole. And we also have 18 hydrogen, which each of them, if you look at the periodic table, is 1 grams per mole. So that's 72. Yep, 72. No, hold on. 96 plus 18. So that's 114, which is what you got, right? Okay, so molecular weight is going to be 114 grams per mole. And again, each carbon is 12, and each hydrogen is going to be 1. And how do you get the number of moles? You have to divide the number of moles, the mass with the molecular weight. So that would be 2,800 grams divided by 114 grams per mole. .5614 so on moles. Alright. So as long as you have everything in terms of moles, it becomes a bit easier to work with. Number 3, use Actually, 4, 9. I assume you guys are done? Almost? 8,600 something grams of carbon dioxide is my final number. See from the front. You get the same thing? Yeah, 8,000 something.
Yes.
Cool. Okay. What are you ready?
The mole to the gram. Can you just into the mole?
Hold on. No. This is the. Can I have a eraser there? We still work here in terms of moles.
Mm-hmm.
So this is not grams.
Not gram. Okay.
We still work in terms of moles. The easy word to remember is that if you're taking 16 CO2, then this is 2 C8H18. So the actual thing that cancels is that one.
Oh,
So the
okay.
unit is still mole.
Jump
And
step.
yeah.
Okay.
And then we're just going to convert the moles to grams. So molecular weight mass over moles. So mass is equal to molecular weight times the number of moles. Yeah. You get that. You're pretty much there. How are you doing on this side?
Good.
Yeah.
I was just grabbing one. Because my notes were all over the place.
Okay.
I did
What's up?
that, so it's gonna be different, but.
Okay. Yeah. Same thing. Yeah. Um. So I think we're pretty much all there. More or less about the same result. And again, for majority of the problem that you get is that one of the first step is make sure that your reaction is balanced. I would say don't assume that the reaction is balanced at all. Just double check. It's actually if you have to take standardized testing, it's one of the things that they just throw you out the reactions and you have to balance it on your own. So it's one of those things. Number two is if you have any reaction at all, convert to moles. Because you can only do the conversion factor with moles. And number three, try to figure out what the question is asking for, whether it's asking for limiting reactant or yield or something like that. And regardless of what the questions are, is asking you to do, majority of the thing that you have to do first is that you need to balance the reaction and convert it to moles. Let's do one last one, but we're going to use the units that we're going to be using the units of concentration, which is more or less kind of the next few pages from your class planner. So what is the definition of concentration, at least in molarity?
Moles per liter.
Moles per, nope, liter. Yeah, molarity or molar is moles per liter. And essentially this is going to be the unit that we're going to be working with majority of the time in chemistry, just because everything is in terms of moles. And specifically, if you want to look at it based on equations, then concentration, I'm going to use majority of the time this bracket C is equal to the number of moles divided by the volume, and the volume must be in liter. Molarity is one of those things that we use all the times in the chemistry lab because it's convenient. Majority of the time our glassware is in milliliters or liters, so as long as you figure out the number of moles by weighing it and then dividing it by the molecular weight, you can then figure out the concentration just using the glassware that you're using. There's actually a bunch more units of concentration that you probably see over and over again. Majority of the time, again, in chemistry, this is the unit that we're using. The other common one, I'm not going to ask you for now, but I do want you to know that it's such a thing as that, is a small b, which is molality. If this is molarity, with an R, the small b here is molality with an L. The definition is similar but quite different. It's the number of moles divided by the mass of the solvent, or I should say solution, in kilogram.
Molality is the number of moles over the
Mass of the solution in kilogram. Now there's a reason why we're using, I should say the solvent, sorry. The definition gets pretty exact. There's a reason why we produce two different ones. You might want to guess why? What's the problem if we just use this?
can't convert it to weight.
Not quite. There's a problem with using molarity all the time. So, what's inside a thermometer? No, not anymore. The newer one, the one that looks red. It's not mercury. No. Less toxic than that, because you don't want kids to break these things and start, touching bromine, which will burn their hand. It's basically just alcohol with some dye on it. So mostly it's isopropanol, I think, or ethanol, depending on the manufacturer. So what you should know is that if you heat something up, or if you work with organic liquids, you can have a slight change in temperature and their volume goes up by quite a bit. So that's the problem with using the units of molarity, is that if you're, say, working with a reaction that changes temperature even the slightest bit, your actual concentration is going to change over time. Because, especially so when you're working closer to organic reactions, in organic reactions, because the solvent that you're using is not going to be water. It's going to be some kind of alcohol or even benzene once in a while. And if you heat it up a tiny bit, the volume is going to go up by quite a lot. So most of the time in the laboratory, in OrChem labs, if you have to take it later on, you're still going to be using molarity. But because chemistry is not just one branch of chemistry. The physicists also learn about chemistry. This whole thing, the volume contractions and expansion drives them crazy. So they just divide it with the mass, because even though the thing is expanding and contracting, the mass remains constant. So it makes it well behaved a bit more, at least when you're doing calculation. So usually if you look at it from most experimental, you'll be using the units of molarity because it's convenient. But if you're taking things into more physical side of chemistry, so you're looking at more quantitative, usually you might want to keep to unit of mass, just because the mass doesn't change over time. There's other units of concentration too that's common. What's ppm? Yeah, parts per million. ppm, parts per million, or ppb, which is parts per billion, is the kinds of unit that you use if you're looking at water quality analysis and so on. And the definition is also fairly straightforward. It's the mass of whatever it is that you're interested in divided by the mass of the solvent times, well, it's a million, so times a million. As long as you make sure that the both unit is the same, then you're pretty good. And then the same thing with ppb, but instead of multiplying it by a million, you multiply it by a billion. So that's one. The other thing that's common is mass over volume percentage. So it's kind of like molarity, but they get a bit lazy. It's the mass of your interested material divided by the volume in milliliter times 100%. Usually you see something like this if you're in health care stuff, just because majority of the time the volume or the solvent that you're using is water. So if a doctor tells a nurse like, hey, can you make me a saline solution, which I guess doesn't happen anymore because it comes in a packet now, it's ready to go. You take the mass of, say, your salt and then divide it by, and you mix it inside in a solution of certain volume, and you call it 1%, 2%, and so on. So it's fairly straightforward. Now I'm putting a bit of a dividing line here in between, because if you work with chemists, you'll realize that most of your unit is going to be in terms of moles, because you want to know what the equivalence, atomic size equivalent. Whereas if you're working with people who are non-chemists, usually you're going to be working with units of mass or one another, just because people understand what is a mass, but it may take a while to understand what is a mole. I'm not going to do this explicitly in the exams and the tests and so on, but you should be able to convert from one to the other, because you're going to be working with both chemists as well as people who are not chemists. So you should be able to convert between one to the other, or any combinations of which one. It's going to be tedious, but I think it's a useful skill to learn. And as long as you already remember what is how to do unit conversion, I think from one to the other is not that big of a deal. But again, these are just some of the units that's common. But again, we're just going to be focusing on this one for now, for the rest of the class, because it's simpler. And then, moving from one to the other, it depends on what subject that you're looking at. So you can do that on your own later on, when you actually have to work with people. So that's that. But the idea is the same as well, which the reason why I'm kind of putting this, introducing the units of molarity, is because majority of the time in the laboratory, you don't work with mass, especially if your material is in liquid phase. So instead, you're going to be working with concentration. So I want you to be able to do a problem that, say, actually, let's do an example problem. Suppose that you have a balanced chemical reactions 2A plus 3B turns into 4C. Why not? So suppose that you start with 100 milliliter of B of solution containing 4 molars of B, and then you mix it with 200 milliliter of a solution containing 5 molars of A. So what is the final concentration of C at the end if the reaction is complete? Right. So types, basically the same questions that we had before with the masses, but now instead of giving you the grams as well as molecular weight, you're given a volume as well as a concentration. But as long as you have a balanced chemical reaction, your goal is still the same. Just convert everything to moles. After you convert it to moles, figure out the limiting reactant, and you go from there. We're kind of it's like half an hour left before the end of the class, so why don't we just kind of try to work on this verbally? How would you approach this particular problem? To moles? What's the equation that you need to use? Can you give me the equation? Because if we start going into numbers, it will take a while. Is number of moles over volume. So we want to find the number of moles. Moles is concentration divided by, multiplied by, concentration times volume. Thank you. So you convert everything to moles. So suppose then you get to figure out the number of moles of A is, you figure out the number of moles of B is done, and the number of moles of A is also figured out. What else do you need to do? Yeah. So suppose that you've already figured out some number with number of moles of A and number of moles of B. What else do you do?
Then you find the
Limiting reactant. After you figure out the limiting reactant, you figure out the theoretical yield. Right. So suppose that you figure out that the theoretical yield of C is equals to some moles. What else do you need to do? Well, in this particular case, we're asking for the final concentration of C. So we're going to try to convert it to concentration.
So you can do the moles of C over
The volume final.
So you have to convert 300 milliliters to liters, right?
Yeah.
And then so if you want C divided by 300.
0.3 liters, yes. Yeah, that's pretty much it. And I was trying to trick you guys there. So here, the final volume, what I want you to notice is that because we mix the two solutions, the final volume is going to be 100 milliliter and the 200 added together. I was trying to trip you out there, but you didn't fall for it. So that's actually one of the more common error that I see, is that if the solution is mixed, sometimes people forget to add the two volumes together. All right, so more or less that's kind of the same problem that you just worked out with the masses, but now we're just using everything in terms of concentration. But the process remains the same. Convert everything to moles first, and figure out what the question is asking for in the That's as quick as we get in terms of solving things. Any questions so far? Nope. I'll keep this page for now, and I'll just use the board a bit. I'll let you know where we're going next week, or at least the beginning of next week, and throughout the rest of the semester as well. The reason why I'm bringing up, do you guys finish this off in terms of copying this down? Yeah? Okay, okay. Then I can just do it with you. So what we're going to do next is we're going to look at equilibrium. And what happens is that it's a simple question. So for example, if I have a weak acid, so for example, a weak acid is, that's not a good one. Hydrofluoric acid is a weak acid. And what happens is that if you mix hydrofluoric acid in water, it will dissociate into H plus and F minus in aqueous solution. And because we're looking at equilibrium, one of the easiest and most common equilibrium that we see is acid-base equilibrium. So this is specifically acid-base. And we're going to be interested in the concentration of H plus in solution. Or the final concentration of H plus. There's a reason why H plus is kind of interesting, is because it reacts with a lot of stuff, and especially in biological system, I would say 80% of the chemistry in your body is basically acid-base reaction. So gotta know the equilibrium with respect to H plus. But the issue is that if you have 10 moles of HF, what you'll find, and you have none of these initially, what you'll find is that only a very, very small fraction of this 10 moles of HF is actually going to produce, is actually going to dissociate. Majority of them is going to remain a interconnected HF molecule. So 99.99% is going to remain like this guy, but a little bit, about 0.01% is going to turn into H plus and HF. F minus, excuse me. So this X here is a small value, and we don't exactly know what it is, and that's kind of what we have to solve. So we're going to try to solve for X using some equilibrium constant value. We'll get to that next week, but that's the reason why I'm kind of going into balancing reactions, and then the amount of reactant and product produced using X's instead of an actual value. And then at some point we're going to convert everything into concentration. So we're going to have to divide everything by volume. So we're going back to concentration. So I'm just going to, we have just a bit more time left.